This video is about parametric equations and corresponds to section 7.1 out of the OpenStax Calculus book, Volume 2. In this video, we're going to discuss what parametric equations are, what they're used for, and how to translate from a parametric equation to a regular rectangular coordinate system equation and back. We'll also talk about some tricks of the trade and things to make it easier to do these calculations using a graphing calculator or an online calculator such as Desmos. First, let's discuss what parametric equations are useful for. Typically, we use a parametric equation for functions that aren't actually functions. In other words, these are graphs or curves that don't pass the vertical line test. Examples of those would include circles, ellipses, hyperbolas, and all other kinds of graphs that, while curves, are not in fact functions. Another equation that is very usefully done with parametric equations are equations where you cannot possibly solve for y. In most graphing calculators, you need to be able to solve for the variable y in order to enter it into the graphing calculator. If you cannot solve for y, then you cannot easily graph it. However, by writing it as a parametric equation, you can graph it. There are other reasons to use parametric equations. One of the primary reasons to use parametric equations is because a parametric gives us something that a regular rectangular coordinate system does not give us. This is the third reason that we use them, and one of the most important. The reason is it can describe the position in either 2 or 3 dimensions with respect to time. In other words, it just doesn't tell you where the point is, it tells you when the point is there. This is something that you cannot get from a regular rectangular coordinate system graph. It only tells you that the point is there. In order to find out when it's there, you would have to do something separate to find the time. When we're looking at a parametric equation, the parameter is an independent variable. Often we use t for time, but we can also use theta for an angle value. These are not the only possible parameters, however. There are lots of different things that you can use to represent the parameter. For us, the most common will be, however, t for time and theta for the angle. When we have a parametric equation, we are rewriting the function which was with respect to x and y instead in terms of the parameter t. T is now considered the independent variable, and both the x and the y equation are considered to be dependent on t. In this sense, as the parameter t or theta changes its values, the x and y coordinates will trace out a path in a particular direction in the xy coordinate plane, or in 3 dimensions in the 3-dimensional space. This means that it not only tells you where it is, but when it is there, and in what direction the particle or the substance is moving. Let's take a look at how to represent a curve in the xy plane parametrically. The equations that are used to define the curve are called parametric equations. Previously, our equations have been single equations written in terms of the variables x and y. In Calculus 3, you'll see equations written in terms of the variables x, y, and z for 3-dimensional space. A parametric equation takes each of the variables that you have in 2-dimensional or 3-dimensional space and writes them in terms of the independent parameter, in our case, usually either t or theta. That means that we can write it x as a function of t and y as a function of t, or both x and y as functions of theta instead. Again, the points x, y are still going to be on the rectangular coordinate plane as they always have been before. T, however, will vary over whatever interval is allowed for the t values. If you're talking about time, you know that time cannot possibly be negative. So the domain for a function where time is the parameter will not exist when time would be less than 0. Typically, we will call this curve a plane curve or a parametric curve. Sometimes it's denoted by the uppercase letter C. However, I will typically simply represent it using the parametric equations, x written in terms of t, the parameter, and y written in terms of t, the parameter. In this sense, a single equation in rectangular form is represented in two-dimensional space by two equations in parametric form. In this figure from the textbook, you have an image which represents the movement of the planet Earth around the sun. You may not remember, but hopefully you do from your college algebra or pre-calculus class, that this is, of course, the graph of an ellipse. An ellipse has a center, it has two major vertices and two minor vertices. It also has focal points, F1 and F2. The focal points help us to draw the perfect ellipse. If you have not studied these, then you will need to review it before we get into conic sections represented as polar curves in section 7.5. You'll notice that the sun is located at one of these focal points. What happens with an ellipse is that any object that is moving about an object at its focal point in its gravitational field will follow an elliptical path. Where the object is on that path, in this case Earth, can be given in terms of what the date is. So for example, if on January 1st, the Earth is here, and on April 2nd, the Earth is here, we not only know where on its elliptical path the Earth is, but also when it is there and in what direction it's traveling. In this case, the Earth is traveling about the sun in a counterclockwise orientation. This gives us more information than a simple XY coordinate graph would give us. It tells us when it's at that location and what the orientation of the curve is, which direction it's graphed in. If you superimpose the XY coordinate system on top of that graph, you would simply have an ellipse plotted there. Because it would be only with respect to X and Y, time would not appear on the graph at all. You would also lose the information about the fact that it is traced in a counterclockwise direction. Now let's talk about how to actually graph using a parametric set of equations. The first thing you typically do if you're going to graph it by hand is set up a table of values. This can also be done on a graphing calculator or an online graphing calculator such as Desmos. Since the independent variable in both x and y is t, we put t as the first column in this table. Yes, it is the independent variable now, but it will not actually appear on the graph. The graph again is only graphed on the xy coordinate plane. The presence of t, however, is indicated in that we will put arrows on the graph to indicate the orientation or the direction in which the curve is traced. The arrows indicate that it must in fact be a parametric equation. The x of t and y of t appear as the second and third columns of the table. Unlike a typical t chart for the xy coordinate plane, which only has x and y, when you're graphing parametrics, you need three columns. The first for the independent parameter t, the second and third for the dependent variables x and y. The last two columns will give you a set of ordered pairs which will be plotted on the xy coordinate plane. Keep in mind that the xy coordinate plane is just the same old xy graph you've been graphing since middle school. And the parameter will not appear except in terms of the orientation. These are represented with arrows on the graph to show which direction the graph moves as the t value goes from the lowest parameter value of t to the highest value of t. There are occasions, though we will not see many, where it makes no sense to refer to the orientation of a parametric equation because in fact it jumps around all over the place. It switches from one side to the other, from top to bottom, left to right, and there is no obvious order. In this case, you simply draw the graph after it is completed, and you don't try to put the arrows on there. As I've mentioned, you can use a graphing calculator such as a TI-83 or a TI-84 or a TI-Inspire, or an online system such as Desmos or GeoGebra to graph parametric equations. In some ways, Desmos is easier. However, in other ways, the graphing calculator is easier to see the orientation. There are some links that I've put here into the video and into the file associated with it that explain how to graph a parametric equation in Desmos. In Desmos, it does not view the parametric equation as having three variables and simply produces the final result of the parametric equations together. In order to see the orientation, you have to be able to add a slider bar. If you will watch the video listed here under Desmos Investigation 3, Graphing Parametric Equations, at this URL, you will understand how to do that. Texas Instruments has a ton of videos and written material on how to do things with their entire line of calculators. You can go to the TI Graphing Calculators models and look for more information on the particular model you have. The activity central for your model will give you different kinds of subject-specific topics and lessons. You can also Google it and look on YouTube. There are literally hundreds of videos on YouTube on how to use TI graphing calculators to graph parametric equations. Most of them are quite excellent. I'll also demonstrate as well. Because of the COVID-19 virus, Texas Instruments is now offering a 6-month limited use of their software for a calculator. Now, this will load directly onto your computer. I haven't tried it myself, but this link will take you to a system where you can choose which of the TI softwares you wish to download, both for an Apple computer and for a Windows PC. This will let you use it directly on your computer in case you do not actually own a graphing calculator. However, you have to activate this software before June 30th to get the free 6-month software license. I'm going to demonstrate how you can graph a parametric curve using both Desmos and a regular TI-84 Plus Silver Edition. The graphing calculator is definitely not the most recent on the market, and it's not the color edition. I will confess the color editions are not my favorite because they take longer to graph, and I find myself being somewhat impatient. I will show you how to do it, but I've also provided some screenshots in the written material which show you at each step what you should be looking for. On each picture, you'll see a red arrow which directs your attention to a particular part of the screen for Desmos. Now I want to pull in the Desmos screen and show you how to graph cosine of t, sine of t, between 0 and 2 pi as our first example. On your computer, go to desmos.com and select the graphing calculator. On the screen, you'll see both a blank graph, you'll see a wrench, which represents some settings, and home, which brings you back to the home page. It also will give you control over the zoom. You can also zoom in and out, of course, by using the scroll bar on your mouse. Up here, we see different options. The gear symbol, of course, will give us the ability to change some things, and we will be using this from time to time. Click into the first box so that we can enter our first parametric equation. The first parametric equation we want to enter is cosine of t, sine of t. Let's take a look again at the equation that we have. We are trying to graph cosine of t, y equals sine of t, with the parameter t going between 0 and, well, let's make it 2 pi. To do this, we need to return to the screen where we have the Desmos brought up. In order to enter something in parametric form on Desmos, you will put it into parentheses, almost as if it were a point. You'll give the equation for the t first, and notice that as soon as I hit t, it immediately asks if I want to add a slider for t. Then I can put a comma, and then I can give the second value, which is y is sine of t, and close the parentheses. Down below, it now realizes that this is in fact a parametric equation. You can click into the box and enter the values for the range that t is allowed. These restrictions are going to restrict the domain on the actual one. You'll notice that the instant I completed typing, I immediately got a picture here on the right. This did not give me the orientation and did not graph it going from 0 to 2 pi. In order to get the graph to do that, we have to do a little bit of a workaround in Desmos. What we're going to do first is we're going to click on the gear symbol above. This gives us a duplicate icon. Click on the duplicate, which will copy the picture down below. Now put your cursor in front of the T and type in A instead. Make sure that you replace all the T's with A first, and then after they're replaced, then click on Add Slider. If you add the slider in the middle, it may not allow you to change them. You'll notice that it automatically has put the range from -10 to 10, but that is not the range for the parameter t. I'm going to click directly on the -10, which will allow me to change this to 0, and on the upper one I can now change it to 2 pi. Note that I can enter pi by typing pi, the two letters. The step is important on both Desmos and on a graphing calculator. The step is how many points it's going to calculate between 0 and 2 pi. For example, let's put in that I want to do a step by pi divided by 2. If I enter pi divided by 2, then it's only going to calculate at multiples of pi over 2 between 0 and 2 pi. That would be at 5 separate points: 0, pi over 2, pi, 3 pi over 2, and back around again to 2 pi. Now if I click on play, you'll see that I don't see anything much different. However, if you look at the picture, notice that the dot is clicking around the picture at the multiples of pi over 2. Now, this is giving me what the graph looks like, but it's not very smooth. If I stop this and I go back and click in here, I can change the step to something else. Desmos will prevent you from producing a very poor picture by giving you the true picture no matter what. The graphing calculator, on the other hand, will not. If you tell it to go from 0 to 2 pi using a step of pi over 2, it will try to connect just those 4 points with a picture. In other words, it will connect here, 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 and back to here. And you'll get something that looks more or less like a diamond or a rhombus. It won't look remotely circular. I've discovered over years of use that one of the best steps to use is pi divided by 60. Now, why divided by 60? I chose something that gives me a lot of data points for the graphing calculator. It also is automatically multiples of pi, pi over 2, pi over 3, pi over 4, and pi over 6. Anything that is a multiple of those is a good value. On the other hand, you might think, well, if pi over 60 is good, then pi over 120 must be better. In some ways, yes, it is better, but keep in mind that there's a trade-off. The more points you give, the slower the graphing calculator goes. In some cases, it goes so slow, it gets hung up, and then you have to restart it. I found that pi divided by 60 gives me a smooth enough curve that I can see what it looks like while not slowing it down so much that it freezes. Now, if you click on the play, you should notice that the circle goes around the dot much more smoothly. It is, in fact, still only calculating 120 points. Notice, however, that it seems to be bouncing back and forth, which would seem to indicate the directions going both ways. That is not the case. In our example, the parameter t starts at 0 and goes to 2 pi in that direction only. Desmos has a slider, and the default is to go both ways. We need to pause it and change that by clicking on the double direction arrow and changing to one direction only. If you click this one, it will keep repeating. Me personally, I only want to do it one time. I usually use the single direction with the one below it so that I can see what it looks like. Let's play this now and see what happens. It's going to start and slowly go around. Notice it picked up from where it left off. If I click play again, though, it's going to start back at the beginning when t equals 0, proceed towards t equal 2 pi, and stop. Let's watch. Focus on the circle. There it goes. Going around and stop. And we're done. There was another option here, which had a dashed line. This will let it play indefinitely. I don't like that one. Instead, I like the once around and quit. Whoa, it seems to have gone nuts. And you'll notice that because I had it open and playing at the same time, it also messed up my limits. So be careful when you're doing it that you don't accidentally change the values unintentionally. You can fix it again. Simply click there, replace that with 0, replace the other value with pi, or 2 pi rather, and then you can click on play. And it should go one time in the direction of the orientation. Now, what does that mean in the direction of the orientation? That means that you should be able to apply and draw arrows here in the direction that it traces. So you'll put arrows on the curve as it comes around in this direction. Now let's do the same thing, but use a TI-84 graphing calculator to produce the graph of cosine of t, y equals sine of t, between 0 and, oops, looks like I forgot the 2 again, 2 pi. Go ahead and turn on your graphing calculator. The first thing we want to check is to make sure that we're in the right mode. Click on the mode button. You'll notice that we are in fact in radians. When we use theta for our parameter, we will always be in radians. The formulas for derivatives and everything else assume that you are in radians. Those formulas are not correct if you're in degrees. The next thing you'll notice is, unlike previously, we're almost always in function. Now we need to move to parametric. Yes, this semester you're going to finally get to use the second one, PAR, and the third, POL. No, we're not going to use SEQ, though we could have when we looked at sequences and series. We're going to look at parametric mode. That is on the TI-84, the fourth line down, and second from the left. Highlight PAR for parametric and hit enter. Once it says PAR, we're ready to go. Now hit the Y equals key. When you hit the Y equals key, notice that the next thing you see is a parametric representation of different formulas. I already have one parametric equation in here, but we'll eliminate it. How do you know that these are parametric? This says x1 and then has an uppercase letter T and y1 with an uppercase letter T. Notice that the dotted line indicating the graph only appears to the immediate left of the variable x, not to the immediate left of the variable y. This pair of equations represents one parametric equation. If I hit clear, it will clear out the first one. I will need to clear out the second as well, since parametric equations in 2 dimensions are given as pairs of equations. The pairs of equations I was looking for was x equal to cosine of t. Hit the cosine button, then hit the variable button. The x, t, theta, and n that you see on that button correspond to function mode, parametric mode, polar mode, and sequential mode. We'll hit that button and it will give me the parameter t. Then I can close the parentheses and move down one and enter sine by hitting the sine key, and then the variable key in parametric mode will automatically give you t. If I close that parentheses now, it is ready to graph the parameter. However, I had limitations on my parameter. My parameter t must go between 0 and 2 pi. Click on the window button, second from the left at the top. In the window, you'll see that automatically it typically goes from -10 to 10. I'm going to change mine to go from 0 for my minimum parameter value to 2 times pi. Remember that pi is above the caret key, so I hit the second button and the caret to get pi. You can see here that I do have 2 pi. The t step is the same thing that we had to use on Desmos. On the graphing calculator, however, choosing a poor step will produce a terrible graph. I'm going to deliberately choose a very poor value just to show you what happens. Moving down, I'm going to take the choice of pi divided by 2. Notice when I move down that the calculator had to estimate 2 pi as about 6.28. Now I'm going to enter pi divided by 2. When I put in pi divided by 2, it's going to use that to step the t values. Again, if I were to move down, it would show me about 1.57. You will see here that you have options for X-min, X-max, X-scale, Y-min, Y-max, Y-scale, and so forth. I typically do not change those. Instead, I let the graphing calculator do the work for me. We're going to use a zoom button. The zoom button is here in the center with zoom on top of it. The one I like is called Zoom Fit. It is usually on the 0 option. If you scroll up or down, you want to keep going until you reach the Zoom Fit option. For me, it's at 0. What the Zoom Fit does is it says, for the range where t goes between 0 and 2 pi, it finds the best possible XY window and chooses the right values for X and Y. I'd rather let the calculator do that part of it for me, since that can be difficult to figure out for some parametric equations. Now I hit Zoom Fit. Ugh, terrible. That is not a circle. We have two problems. First, when I click Zoom Fit, it does give me what it thinks is the best window, but it's not a square window. The window on the TI calculators, except for the Inspire, is unfortunately a rectangle and not a square. You can fix that by hitting Zoom and Square, which is option 5. That will make the distance on the x-axis the same as the distance on the y-axis. This is still not a circle. It is, however, now a square. What's the problem? The problem is that I told it to use pi over 2 for my step. So it calculates one value at 0, one at pi over 2, one at 2 pi over 2, 3 pi over 2, and back around to 4 pi over 2. Then it tries to connect the dots. It thinks like a 3-year-old. If you want to have a better picture, you need to give it more points. This is the reason for the t-step. And this is the reason I typically use pi divided by 60 for my t-step. We'll go back down to t-step and we'll change our t-step to pi divided by 60. When I enter that and I go back to the graph, let's watch what happens. Aha! Not only is it now graphing it, but you could see clearly what the orientation was. You saw it started on the positive x-axis, traced it in a counterclockwise direction, and ended up back where it started. There is something on the graphing calculator to help you see this, and you can graph it over and over again. Go back to the y equals window. When you scroll to the left of the x1t, you can put the cursor above the 3 dots which show the graph symbol. If you now will hit enter repeatedly, you can get different options for how to represent the graph. When I'm doing parametric and polar graphs, I always leave them in the following mode. This to me looks like an old-fashioned key. It's actually a hyphen and then a 0. What it means is it's going to draw the line and represent the point where it is at that point in time with a circle. Now let's hit graph and watch it graph again. See the circle? The circle represents that value of t, the parameter, where it is in the xy plane at that moment. It will draw the circle in the correct orientation, and then it will stop at the highest t value. Again, I always leave it in what I call key mode, which is the hyphen followed by the 0. There is no mode like this on Desmos, and this is one of the reasons I like to use the graphing calculator. Let's look at example 3 now. Let's graph the parametric equations x equal t squared minus 4 and y equal t divided by 2, with the parameter going from -2 to 3, again using the TI-84. Go back to the y equals button. If you want to leave your previous one in there, put your cursor on top of one of the equals for the parametric pair of equations and hit enter. It will turn both the x equation and the y equation for that parametric equation off. Now let's enter the formula we're looking for. T squared minus 4 is the x equation with respect to t. T squared minus 4. For the y equation, I have y equals t divided by 2. My parametric equation, this time, the parameter is going to go between -2. Make sure you use the negative at the bottom. Do not substitute a minus in place of it. -2 up to 3. The step here is less important because it is not being used as the argument to a trig function. However, I do still want a fairly good number of points. I may just leave it here at what was pi divided by 60 and see if it gives me a decent enough graph. Every time I graph a parametric or a polar equation, however, I want to let the calculator figure out the best screen for the x and the y coordinates. So I'll go to zoom and then I'll enter 0. That gives me zoom fit. It will take it a while, and I'll get to here. Keep in mind that this graph is not squared off. If you want to know what it looks like on a square graph where there's no distortion, you need to then square it, and it will regraph it. Also remember that I can watch it graphing if I put it into the key mode by coming down to the equation, moving to the far left of x of t, and highlighting and hitting enter until I see the -0 representing what I call key mode. When I graph now, you can see the key, which started on the negative y-axis, comes around, looks like it hits the point -40 on the x-axis, and continues graphing what appears to be a right opening parabola tracing from the bottom around in a clockwise direction towards the top. I would indicate this on the graph with arrows. Let's now look at the same exact parametric equation on Desmos. Starting at desmos.com/calculator, I need to enter the parametric equations. The parametric equations that I was given were x equal to t squared minus 4. Click in the first box, open up parentheses, put in t to the second power minus 4. Then when you put the comma, the option to add a slider will disappear as it now understands that you want a parametric equation, t over 2 for the y value. Our parameter goes between -2 and 3. Enter -2 for the lower value of the parameter and enter 3 for the upper value. Again, Desmos will give you instantly what the parameterized equation looks like in the xy coordinate plane. It does not, however, automatically give you the orientation. To get around that, we're going to click on the edit list, copy the equation, click into the equation where the variable is and replace the t instead with a. Now when I have it replaced with a, then I will click on Add Slider. For the slider at the bottom, you'll see that it automatically goes between -10 and 10. My slider needs to match the values on the parameter. Let's see what that would be, between -2 and 3. If I extend the screen up so you can see a little bit more, I'm going to click on the -10 and replace it with -2. Click on the upper end and leave it 3. The step is up to you, but again, I often just simply use pi divided by 60 for all of my parametric and polar equations. Remember that we need it to graph in the correct orientation, which is not backwards and forwards. We need to get rid of the double direction arrow and replace it with the one direction one time arrow. Now when I click play, it should finish playing and then be done. When I click play again, it will start at the beginning and then it will play one time in the correct orientation. Be sure that you add the arrows onto the graph as they should appear to indicate the orientation. Example 5 is a rather strange example and something I alluded to earlier in this video. Take a moment to pause the video and enter the graph of x equals sine t, y equals sine of t squared into the graphing calculator with the value for t between -10 and 10. Then restart the video. Once you have it done, then go ahead and let's take a look at the graphing calculator. In the graphing calculator, you should now have something that looks like this inside of your y equals. I'm going to go ahead and place the cursor onto the dotted lines representing the graph to the left of x. I'm going to make it into the key symbol by hitting the enter repeatedly. Once I have the -0, then I know that I've got the right character in order to watch it graphing with an open circle at the parameter as it moves around the XY coordinate plane. I know that I need to set my t values to go between -10 and 10. So next you should click on Window. Make sure that you're between -10 and 10 and choose a small enough step that you'll get a good picture. I tend to leave mine on pi divided by 60. The next thing you want to do is hit the zoom button. The zoom button will give you the option to fit the XY screen for the best possible choice for that range of parameter values from -10 to 10. You'll see in the upper right-hand corner up here the 3 lines that keep moving. That lets you know that it is doing something. In this case, when you're looking at it, it's producing, well, it's a little crazy what's happening. And it doesn't really look like I can tell too much what's going on, except that when it keeps going, oh my goodness, what is going on? This is not an obvious picture, and there's not really an obvious orientation for it. It's hard to see what's happening. Let's try looking at it from a different point of view. Do you see that it keeps tracing and tracing and tracing and tracing? There's no obvious orientation here and no obvious graph. If you allow this to go long enough, it will eventually fill up the screen where all the pixels will be black, and it will be very difficult to actually discern what the orientation is. Let's take a look at a slightly different example that does something similar and yet a little bit different. If you want to interrupt the graphing calculator in the middle of graphing, simply hit the on button again, and that will interrupt the cycle in case you get it stuck into a cycle where it's computing too many points. Again, hitting the on button one time will interrupt the cycle. Let's go back to our formulas, and let's, instead of having sine of t squared, make it the sine of t quantity squared. Let's see what that kind of graph would produce in our picture. Coming across now, I need to eliminate the square. So I can hit the delete key when I'm on top of it. You'll need to hit it twice, once to delete the 2 and once to delete the power. Now I need to put parentheses around the sign of t. In front of the sign, put it on the S, then hit second delete to get insert. Hit the open parentheses. Scroll to the far right and add a parentheses at the end. Now hit the square button, which will square the whole thing. Let's go back and hit graph and see what happens on this particular graph as it tries to graph from -10 to 10. We can see that it's graphing and it looks like it's giving us part of a parabola. And then it looks like it's coming back and it's going to scroll backwards and it hangs up at the top and then it comes back and then it moves forward and then it moves back and then it moves forward. In other words, it's graphing this out multiple times. Keep in mind that we consider that when a parametric curve graphs the same shape over and over, we consider it to be different from the parametric curve where it only traces it once. What this is showing is that a particle is repeating the path more than one time. There is a big difference between taking your car and driving down to Colorado Springs one time and taking your car and driving to Colorado Springs back and forth 5 times in a row. Those are not considered the same parametric curves, though they are, of course, related. Let's take a look at something else. For example 6, I want to take a look at the first one I did, the parametric equation x equals sine of t, y equals sine of quantity t squared for t between -10 and 10 using Desmos. The one advantage of Desmos is I do not have to wait for it to finish graphing. You'll see immediately that what has happened is it's produced this, well, black blob in the middle. When I run the t values from -10 to 10, it scrolls back and forth and back and forth and back and forth. Yes, I could copy it and I could paste it down below and then I could make a slider bar for A. To do that, remember you must replace both of the t's first with a's before you can click on Add Slider. When you add the slider, you want the orientation of the slider to match the orientation of t from -10 to 10. We want to only graph in the forward direction, and I think in this case, once will be enough. Since this one is going to be graphing for a very long time, we could actually increase our speed and make it go twice as fast. Let's zoom in a little bit on that spot so that we can see a little bit more of the detail. If I zoom in, you can see that in fact it's not really a black blob, that it does look like it has that parabola that we had on the other. If I had allowed it to keep going, I would eventually have gotten the same thing. Let's move our slider all the way to the left end, and you'll notice it gives me a black ball wherever it's starting. You can change the color if you want on the slider by doing a long left click. Let's make it red so we can see it. Now I'm going to click on Start and watch the red ball as it moves around. Whoa! What on earth is happening? Let's slow down the speed a little bit and see if we can tell what's actually going on. Let's go at half speed now. Let's click back to the slider bar and move it back all the way to the far left to -10. Now click play. Holy smokes! It is in fact in some ways going smoothly, but in other ways it's jumping around on the graph. Remember I mentioned earlier that there are some parametric equations where the orientation doesn't really make sense because it's jumping around. Let's do it one more time and we'll slow it down even more to see if we can see how slow this thing is going and see if you can detect when it is jumping around. It looks smooth there, and then it looks smooth. Is it smooth the whole time though? Or does it eventually start jumping? You can see it's going slower as it reaches this part, much slower, and then it continues this path. Sometimes they jump around and do not compute any points at interior values for the parameter. It's possible that the parameter is not defined at some values. In that case, the orientation may not make sense. On one such as this graph, the orientation would be more confusing than anything else, since it retraces and overtraces its path so many times. The next thing we want to talk about is how do you create a parameter when there is no parameter? In other words, what if you have a normal equation in x and y and there's no parameter t present, but you want to parameterize the equation? That is called a parameterization of the curve. Again, the curve could be a function, but it's not required to be. The simplest way to allow us to create a parameterization of an equation is to let either the variable x or y be the parameter t, and then to rewrite the equations in terms of t. Keep in mind that parameterizations are not necessarily unique. There could be more than one representation for the exact same curve. In fact, for some curves, there are infinitely many representations. Let's take a look at an example. This is example 7. We want to give two parametric representations for the equation of this parabola. This parabola has a vertex at 2, 1. It opens up because the leading coefficient is positive. What is our first choice? Well, the easiest way to create a parameter is simply to let x be t and rewrite the two equations. Let's do that now. If x is going to equal t, that would be the first of my parametric equations. Then I will write my second parametric equation, which will be y as a function of t, by replacing the variable x with t. I know it sounds stupid, but this is in fact a parameterization of the equation. You're not required to put the single brace to the left, but I like doing it to indicate that together the pair of equations x of t equal t and y of t equal to the quantity t minus 2 squared plus 1, together they represent one parametric equation. There's another obvious way to parameterize this one. We could instead take the inside to the squared thing, which is the binomial x minus 2, and let that be t instead. In the second choice, if we want to use that parameterization, it will look a little bit different. If x minus t equals 2, then that implies that x is equal to t plus 2. That gives us our first parametric equation. X as a function of t is t plus 2. Now, in order to parameterize it, I need to be able to replace the y with this representation. Remember that this is the variable x, so to get the other parameter, we simply need to replace x with t plus 2. In that case, let me scroll down, create a little bit of space here. If I'm going to replace it, then y as a function of t, which is at the moment x minus 2 quantity squared plus 1, would become, replacing x with t plus 2, will give me t plus 2 minus 2 quantity squared plus 1, which is, of course, just t squared plus 1. In other words, my parametric representation with that substitution would be x of t is t plus 2 and y of t is t squared plus 1. I could play this game for any constant value, not just 2. And since I can do that, that means that I could represent this graph in infinitely many different ways. It would, however, in every case produce exactly the same picture. And that is the beauty of the parametric representation. What if I want to go the other direction around? In other words, I have the equation in parametric form, but I want to get it back into rectangular form, where the only variables involved are x and y. This is the process called eliminating the parameter, where you remove the t from the parametric equations and result in only an equation in x and y. You may be wondering why we might do this, since it would remove the orientation from the curve and would also hide the restrictions on the domain based on the allowed values of the parameter t. The advantage to doing this is that sometimes it will help us identify what the parameterized curve looks like. In other words, we'll be able to more easily tell that it's a circle, an ellipse, or a hyperbola if it were in its rectangular form. And the reason is simply because we're more accustomed to rectangular form. The simplest way to do this is to solve either of the parametric equations for the variable t. Then be sure to substitute it into the parametric equation you have not used yet, and then solve for y. This may not always be possible, since parametric equations are sometimes used to represent equations for which you cannot solve for y. On the other hand, when a trig function is involved, we often will, instead of solving for the parameter t or theta, we will instead isolate the trig function, such as sine of theta or cosine of theta, in both the parametric equations. Then we use a Pythagorean identity, such as sine squared plus cosine squared equals 1, to eliminate the parameter. Let's work a couple examples that demonstrate these two different methods. In example 8, we want to find a rectangular equation for the plane curve given by the parametric equation x equal t squared, y equal 2t plus 3 for t on the restricted domain from -3 to 3. Notice that even though we have listed two equations, we still consider this to be one single parametric equation. In order to do this one, the simplest thing to do would be to solve for t. It would be difficult or more difficult to solve for t from the x variable because t is squared. Instead, let's isolate t from the y equation and substitute that value of t into the x equation. This is what we would get. If we were to do that, I would take the equation y equals 2t plus 3, and then I would solve for t. This would give me y minus 3 equals 2t, and dividing both equations by 2 would finally leave to t equals y minus 3 divided by 2. You could also write this in the form of 1/2 y minus 3/2, or y divided by 2 minus 3/2. Any of these is perfectly fine. Once you have solved for it using the y equation, you must, however, plug it back into the x equation. You are required to use both equations when you eliminate the parameter. So now we're going to place it into the x equation. Putting it into x of t will lead to the following. Since x is equal to t squared, I replace what is in the parentheses t with instead y minus 3 divided by 2 quantity squared. That would be my preferred way of writing it. You may prefer a different one, and that's just fine. To continue, this would give me x equals the quantity y minus 3 squared divided by 4. I could also write this as 1/4 times the quantity y minus 3 squared. If I want to then solve this one for y to get an equation in x and y in a form where I could put it into the graphing calculator, I would need to isolate the y. In order to do that, however, I would have to isolate the thing being squared and then take the square root. Because that would require plus or minus, I know instantly that this thing cannot in fact be a function. It must in fact be a sideways parabola. And of course it is. We'll be studying this kind of equation more in depth in section 7.5, conic sections. For now, however, you could leave it in this form. You could also write it in a better form, which is 4x equal to y minus 3 quantity squared. This is the form that we'll use more often in section 7.5. It is a course equivalent to solving for y. Let's solve for y so you can see what it would look like. Creating a little bit more space for me to work, I would have to take the square root of both sides. When I take the square root of the side without the square, I know that it could be positive or negative. That is going to result in y minus 3 being equal to plus or minus the square root of 4x. 4 is a perfect square, so the 2 pops out, and I would finally get y in terms of x, but in fact, since it's not a function, I should not use function notation and should instead simply write y equals 3 plus or minus 2 square root of x. The only issue with this form is that nowhere in this form or this form or this form does it indicate that there is a restriction on the domain. There was a restriction, however, which is given by the restriction on the parameter t. T goes between -3 and 3, which means it's not going to graph the entire parabola. In order to know where it's going to be restricted, you would have to take the t values and plug them in for x and or y to determine where it starts and where it stops. On this example, if I replace t with -3 in the x-coordinate, -3 squared will give me 9. This means that it is in fact going to start at the ordered pair, which has 9 for the x-coordinate. Plugging -3 in for t in the y equation would give me -6 plus 3, which is -3. That means it starts at the ordered pair 9, -3. Then it will graph towards the point given by 3 for the t value. Then when I plug it into x, it again is going to stop when it reaches 9 for the x-coordinate again, but for the y-coordinate, 2 times 3 is 6, plus 3 is 9. That tells me that it's only going to graph between those 2 points. If you want to know some of the points in between, you could take some of the values in between to see where it's going to graph. This makes it more difficult to find the restriction on the curve. The restriction is more easily seen in parametric form, but sometimes recognizing what the curve is more easily seen in rectangular form. Now let's look at the next example. In this example, we want to find a rectangular equation for the plane curve, which is given here in parametric form. X as a function of t is 5 cosine of t. Y as a function of t is 2 sine t. T takes on the values between 0 and 2 pi. Since these involve trig functions, what we're going to do instead of solving for t, which would involve arc sine or arc cosine, is instead we're going to isolate the trig functions sine t and cosine t. This means that x divided by 5 is the cosine of t, and y divided by 2 is sine of t. Then I'll use the Pythagorean identity that sine squared plus cosine squared of any value, in this case t, must be equal to 1. Using the Pythagorean identity and substituting in the values, I can replace sine squared of t with y over 2 quantity squared. Then I can replace cosine of t with x over 5, and I'll square that. Once I have these two written down, the next step is relatively easy. This simply leads to y squared divided by 4 plus x squared divided by 25, which equals 1. This is clearly the equation of an ellipse centered at 0 and that has a major axis 5 long, 5 to the left, 5 to the right, or 10 long, and a minor axis that is 2 up and 2 down, or 4 wide. In other words, it's easy to see it's an ellipse in this form, but the restrictions are easier to get in the parametric form. In this case, if we're trying to find the limitation on the graph, we would need to plug in the parameter 0 in place of t in both of our parametric equations. This would give us our starting and stopping points on the curve. This is going to start when t equals 0. Cosine of 0 is 1, so the x-coordinate will be 5. Sine of 0, however, is 0, so the y-coordinate is 0. Then it will graph in the direction of increasing t until we reach 2 pi. Because 2 pi is the same value as 0, however, this means that it is going to stop at the same point. While it is difficult to tell, after some experience with parametric curves, you'll come to see that this must mean it traverses the curve one full time. In other words, this is going to graph our ellipse one time all the way around. If we were to draw it, it's going to come out here to 5 and to -5, and then go up to 2 and down to -2. It will start here, where I usually put an S, go up and hit here, come around to here, then to here, and then back to here. We indicate this, of course, with the arrows. And yes, I know, I drew a terrible picture. If your picture is at least as good as mine, then you're doing great. Let's go on and take a look at the next piece of information. The next piece of information deals with what are called circular parameterizations. Now, I'm not going to expect you to memorize these. If you want to write the formula down on a formula sheet, I am okay with that. And yes, you're allowed to say that it will trace the circle counterclockwise if the value of b is positive, and clockwise when the value of b is negative. This should make sense to you since we consider counterclockwise to be the positive direction and clockwise to be the negative. In this equation, as you may remember from your trig class, the magnitude of the variable b is actually the angular velocity. Angular velocity is the rate of change of the angle theta with respect to time. Normally, we talk about linear velocity, which is the change of position with respect to time. But when you're moving in a circle, it doesn't make sense to talk about change of position since you're always on the circle. In that sense, we often talk about angular velocity instead. A, of course, represents the radius of the circle. All equations of this form are circles. Let's take a look at another common type of parameterization called a cycloid. The cycloid gets its name from basically, well, bicycle wheels. Or you could think of them also as unicycle wheels, but I've never been able to ride a unicycle. This is what the parametric equation of a cycloid looks like. This is a very common function type to study in polar curves, has lots of natural applications in the real world. You can imagine sort of what might happen. I wish we could be in class because I could show you an example of a cycloid I've created out of a hoop and a piece of paper and a marker. If you were to take the spokes on the wheel and you were to place a marker, say, at a particular point on the wheel, as the wheel rotated, it would create this sort of bouncing graph that you see here in the blue. That's called a cycloid. This one is created by putting the marker on the edge of the rim of the wheel. You will get different shapes if you put it at different points along the spokes of the wheel. Now, we can take that same equation and we can now imagine that instead of going on a straight road, as in the picture here, that the wheel instead moves along the inside of a larger wheel, like a cog inside of a gear. If you're looking at that sort of situation, you could end up with something that looks like this. In many ways, I think of this as sort of the old spirograph things that I used to play with when I was young. In those cases, you would take out some different shape, put your pencil through a hole, put it inside of a circle with notches cut out of the side, and keeping the inner part along the edge, you would go in a circle around and around the outer circle. In other words, if you're looking at this, the green circle here is staying inside of the blue circle. You also notice that there is another teal colored circle on the inside. That's where the center of the small circle goes at all points. It'll simply trace out another circle. But if you put your pencil in a hole along the edge of the circle, it will trace out what's called a hypocycloid, which is sort of like a cycloid on steroids. Putting it in a different place on this inner gear or inner cog will give you different shapes. You can also produce what are called space-filling shapes. In a space-filling shape, it will literally, fill up the space. This is the general equation here for a hypocycloid. I definitely don't think you need to write this down even on a formula sheet. I'm certainly not going to give you any hypocycloids on an exam. However, I do think it's fun to talk about and fun to think about. Keep in mind that the radius of the larger circle is A and the radius of the smaller circle is B. In our picture, there are really only two circles, the larger one, which is blue on the outside, and this little one, which is green. This inner circle here is the trace made by the center of the small circle as it moves around on the inside of the outer circle. When you look at that, that means that the center of that wheel is traveling along a circle of radius A minus B. The ratio of the outer circle to the inner circle, the radius of their, or the ratio of their radii, is related to the number of cusps on the graph. By cusp, of course, we mean the pointy parts here. When you're looking back at the picture of the bicycle wheel, this point here becomes a cusp, and if the wheel were to continue to roll, this would also be a cusp. If you allow this to continue happening and that ratio is an irrational number, then you will end up with an infinite number of cusps so that it never returns to its actual starting point. This would be an example of what's known as a space-filling curve, as I mentioned before. In a space-filling curve, if you were to continue moving the inner circle around the outer circle forever and ever, you would eventually have a completely filled in circle, solid color. If you don't do that, however, if it's not that, you will get different kinds of shapes. You can see here that in A over B, you have the square root of 2, which is producing the beginnings of a space-filling shape. Here's another one where the ratio of the two is pi. In these cases, of course, they stopped at a particular value so that you could still see the shape that's produced. Hypocycloids can produce gorgeous shapes, and you often see something based on a hypocycloid in all kinds of stained glass windows and lace and other images. I hope that you've enjoyed learning about parametric equations, since we will be using parametric equations for the first 4 sections, 5 of Chapter 7. The first 4 are heavy on the parametric form, with the 5th one less heavy on the form and more focused on representing conic sections as parametrics. The first 2 sections of Chapter 7 deal with just parametric equations, whereas the second 2, 7.3 and 7.4, deal with what are called polar curves. Polar curves are, in fact, parametric equations, where the parameter, instead of being t for time, is theta for the angle. Because they are used so often, they get their own sections, and on a graphing calculator, they have their own mode. This is the end of this video. In the next video, we'll be looking at how to do calculus and derivatives with parametric equations.